Okay, so let's do some analysis on this bearing we're talking about here. Journal bearing 5 inches in diameter, 2.5 inches long, and it's carrying a load of 1 ton, 2,000 pounds, rotating at 5 revolutions per second. So, let's start off, get our N is equal to 5. Looks more like an S5 rev per second. Our P value there, 2,000 pounds divided by divided by 5 inches times 2.5 inches. That gives us 160 psi. The other thing that we need to go into the Sommerfeld number is the R over C ratio. So we've got the diametrical clearance here. Again, for the actual bearing, we're not worried about kind of other bearings of similar design that might have slightly different tolerances. This is like actually measuring out what we're getting. So 0.067 inches is its diametrical clearance. So again, just keep in mind that the Sommerfeld number uses the radial clearance, so they want R over CR. That's going to be equal to the diameter over the diametrical clearance, right? So that'll be equal to, our diameter is 5 inches, and our diametrical clearance 0.0067 inches. That gives us 746. So the only other thing we wouldn't have in our Sommerfeld number is our viscosity. So what we do know is that we want a safety factor of 2 with regards to maintaining that minimum clearance of 0.004 inches that's maintained. So again, this is this is based upon the generally recommended guideline of the 0.002 inches plus 0.00004 times the diameter. Of 5 inches. So we're basically trying to just maintain a relatively decent H naught when we're in operations, even if the load doubles. So basically, if we want to have an H naught that is equal to 0.0004 inches. So if we want that H naught, then that is going to correspond to a particular Sommerfeld number, and it's based upon this chart here. So we've got our minimum film thickness variable, the H naught over C. So if we want that H naught at the condition where we have the double load, then essentially we just need to keep in mind that we'll call this when we're doing that calculation, we need to basically double our psi there. But our H naught over C, and again that's CR, that's going to be 0.0004 divided by 0.0067 divided by 2. Got to keep in mind we're converting the diametrical clearance to radial clearance here. So that'll be 0.12. So of course 0.12 will be, that's this line right here. So that, and we are working in this case, got an L over D ratio of 2. So if we have an L over D ratio, sorry, no, we have an L over D ratio of a half. Length over diameter, not diameter over length, Greg. So 2.5 divided by 5, that's a half. So that we're looking for this line right here. So let's zoom in a little bit here. We are looking, it looks like the intersection is, right there, that's close enough. So let me see here. So it looks to me like, so this is the 0.04, so we're just above that. So yeah, that'll be 0.045, looks like. So there's 1, 2, 3, 4 divisions between the 0.04 and the 0.06. So 0.045 is going to be I'm going to call this S overload. 0.45. Oh, sorry, 0.045. Don't want to be missing. There we go. Actually, let's just redraw that. 0.045. So in that instance, that'll be equal to our R over C squared times our viscosity, which is as of yet unknown, times our rotational rate, 5 per second, divided by our P overload. So again, we're doubling this. So 160 times 2, 320 pounds per inch squared. So solving for our viscosity, what sort of viscosity would we need to have in order to attain this condition? That'll be equal to 0.045 times 320 pounds per inch squared divided by 746 squared times 5 per second. So what do we got here? 0.045 times 320 divided by 740. Let's throw some backers on that. 746 squared times 5. So that'll give us 5.2 times 10 to the negative 6. I guess so it'll be psi seconds, or pound seconds per inch squared. So we can just kind of rewrite that. Pound second per inch squared is a rain. So we're looking here at 5.2 microrain. So going to our charts for the temperature and viscosity curves. So we're looking, we had stated at the top here that a suitable that the average film temperature on the oil is going to be maintained at 150 degrees Fahrenheit. So, if that is the case, then we are looking at a line right about here. Oh wait, 150. Other side of the 140. There we go. So 150, and it needs to correspond to 5.2 microrain. So yeah, we're just above the 5. So essentially what we're going to need to do here is we need something, in order to maintain that that H naught, that minimum film thickness, we need something that is at least as viscous as this. So we're gonna kind of need to round up, and we're gonna need to go with the SAE 50 oil. So if we're using the SAE 50 oil, oh, I don't want to move that side to side. Going with SAE 50 oil, then let's see. Let me just kind of get the intersection. So we're looking right about there, which looks to me to be I think we're probably on the 7 microrain, probably. So select SAE 50 oil, 7 microrain. Oh, what did I do here? There we go. So we got our, now that we've got that, we can find out what our S value would be for the actual operating conditions. So our S actual, that is going to be equal to our R over C squared. So 746 squared times our rotational rate, 5 per second, times our viscosity, 7 times 10 to the negative 6 pound per inch squared seconds, all divided by our p-value of 160 psi. That's pounds per inch squared. So our pounds per inch squared cancel out, our seconds cancel out here, and we're left with a nice dimensionless number, which is what we expect. 746 squared times 5 times 7e negative 6 divided by 160. That gives us 0.12 for our S value. So, yeah. So moving back to our film thickness chart here, we're looking at 0.12 for our S. So again, we're still within the optimum zone during our normal condition. So that's that's certainly good. We want to be, we want to be somewhere within this, somewhere within this range here. So let's go ahead and figure out what our film thickness is at that point as well. So that's this line right here. So 0.24 is going to be our film thickness variable. So multiply that by our radial clearance. And it gives us H naught's going to be equal to 0.0008 inches. So from there, let's see, we want to figure out what the frictional power loss is next. So frictional power loss, again, will be based upon our coefficient of friction variable here. So this line right here intersects this line right here. So let's see. The coefficient of friction variable to me looks to be like it is about 4.2, maybe 4.1. Let's go with 4.1. Again, we're not exactly, when we're reading the stuff off the chart, we're in the right ballpark, right? We're not exactly getting to 3 significant digits here. So if our coefficient of friction variable, that's R over C times F, that is equal to 4.1. Therefore, our coefficient of friction is going to be 4.1 divided by the 346. Sorry, 746. 0.0055. So as we saw before, relating the coefficient of friction to the kind of the power lost, that's going to be H is equal to the load times the radius times the rotational speed times 2 pi in order to get it into radians per second times F. So our load was 2 tons, 2,000 pounds. Our radius it was a 5-inch diameter shaft, so our radius there is 2.5 inches. Our rotational speed was 5 revs per second, and then 2 pi radians per rev. And then our F there, 0.0055. So what do we got here? 2,000 times 2.5 times 5 times 2 times pi times 0.0055. So that's given us 864 pound inch per second. So 865 pound inches per second. If you want to convert that to more common units, then what you might want to do is convert it to horsepower. So keep in mind that 1 horsepower is 550 pound-feet per second. So 464 pound-inches per second divided by 12. That gives us 72 pound-feet per second. So divide that by 555, and we're left with 0.13 horsepower. So the next thing we were asked for was the amount of oil flow through the bearing. So we're going to go to our handy dandy oil flow variable chart here. And again, we are still working with our 1.12 bearing characteristic number. And that intersects with our L over D line of 1/2 up here, right at this line, which that is going to be 5.3 is going to be our flow variable. So 5.3 5.3 is equal to our Q divided by R NCL. For solving for Q, Q is going to be equal to 5.3 times our radius, 2.5 inches, times our N, 5 per second, times our clearance, 0.0067 divided by 2, times our L, also 2.5 inches. So 5.2 times 2.5 times 5 per second times 0.0067 divided by 2 times 2.5. So that's given us a value there of 0.55 cubic inches per second. So that's the total flow kind of entering the wedge. Some of that doesn't make its way through, so we need to look at the next chart for our side flow variable, or a flow ratio, I guess is what they use for this. So right here, this line is our Sommerfeld number. Right here is our variable number. Moving on over, so that to me looks to be 86%. So that's the amount that doesn't make it to kind of circulate around. So our Q side is equal to 0.55 inches cubed per second times 0.86, which is equal to 0.48 cubic inches per second. So that's the amount of flow for the oil that kind of needs to be cooled before it gets resupplied to the bearing in order to maintain the temperature that we had talked about for the average film temperature of 150 degrees Fahrenheit. Now again, that's the average film temperature in the bearing. So we also want to find out what the temperature rise is through the bearing. So our delta T there is equal to the amount of the rate of heat generation divided by our flow and the specific heat capacity. The higher the specific heat capacity, the less temperature rise you get, because you need more energy in order to heat up the oil at a particular amount. The more flow you have, the less temperature rise you get, because there's more material that is getting that heat pumped into it. And obviously, the more heat generated, the more temperature rise you get. So our H, our heat generation rate, that is the 864 pound-inches per second. Our Q value here, 0.55 inches cubed per second. And then a typical value for an SA grade oil is, for the heat capacity of an SA grade oil, is 110 pounds per inch squared degree Fahrenheit. So the pounds cancel out. These inches squared cancel out all but one of those inches, and that inch cancels out that inch. The per seconds cancel out. When we divide out this degree Fahrenheit, it moves up to the top. So we're left with temperature rise in degrees Fahrenheit. So 864 divided by 0.55 times 110. That gives us a 14 degrees 14 degree Fahrenheit temperature rise, which is not unreasonable. The last thing that was asked for was the maximum pressure. So we'll go to this chart here. This is our pressure ratio. So our P divided by the our P divided by the P max. So in this case, again, the nomenclature, this large P here, that's the bearing. Oh, I guess you can't quite see that. This large P here, that's the bearing pressure, or the bearing unit load, and then our P max is the pressure in the film. So again, for our 1.5, so our 0.5, our half line here, we're looking at right about here. So that'll be just, let's say, 0.281, 0.282, why not? 0.282 is equal to large P over P max. So solving for P max, that is going to be our 160 psi, which is the load divided by the bearing projected area, divided by 0.242282. That'll be 567 psi. And I believe that's the last thing that the question asked of us. So there we go.